So, bad injury. Bad angle. No, I look terrified. All right, let's get this review. What am I making? A review video? Practice video? Let's get this YouTube video made. I don't know. So, do you know how to make a good intro to a video? I don't. Coming in live from the command zone over here. I'm gonna make a review video about how to do all those multiple choice. Nope, not multiple choice. I'm distracted by the spinning background clearly. I'm gonna make a review video on how to do all those free response questions. So make sure you pay attention and please make sure you use all your units. Stop losing all those points. All right? All right, let's get into it. Like, subscribe, comment. You know what to do. Boom, we're here. All right, so let's just start with the first question. We'll go through all of them today. But you start with this one. We've done this in class, but we'll do it again here. You can pause at any time. Get the cursor out of here. Anyway, you have a 615 kilogram racing car. Totally different than a race car, obviously. So our mass is equal to 615 kilograms. It completes one lap in a time of 14.3 seconds. So t equals 14.3 seconds. Around a circular track, that's good to note, uniform circular motion. And the radius is equal to 50.0 meters. All right, and it's going at a constant speed. Sweet. So constant speed, remember, is different than constant acceleration. So constant speed means we're going at, 20 miles per hour. A constant velocity means we're going 20 miles per hour west. Here, we're clearly, because we're going in a circle, constantly changing our direction. So as we go around and around and around, our acceleration and force is used to change our direction instead of our speed. So we are still accelerating. So they say, find the centripetal acceleration. So I go to my reference table and I find this equation here. So AC equals V squared over R. And I know R, but I don't know V. So this one's tricky. We got to remember we're going around in a circle. So there's our circular track. And we're going around and around. So if I want speed, this is the first equation we learned. Speed is just distance over time. But I need to remember that my distance is actually the circumference of the circle. Because I'm going around. It's not my radius. I'm not traveling my radius. I'm traveling the circumference. So that's what I'll need to solve for first. So I do 2 pi times my radius of 50.0 meters divided by my time, 14.3 seconds. And this will get me my velocity. I'll grab a calculator. 2 pi times 50 divided by 14.3. I get a velocity. I will just, I'm keeping, no, they want 3 digits. Oh, so 22.0 meters per second after it rounds. So now that I have velocity and I have radius, I can finally answer the question. It's a little bit roundabout. 22.0 meters per second squared divided by 50.0 meters. I'll solve 22 squared divided by 50. I got 9.68 meters per second squared as my acceleration. Sweet. On the next question, what force must the track exert on the tires to produce this acceleration? So the force is the friction force. But let's find the magnitude. So we go and we try to use our friction force equation from the reference table, and guess what? It doesn't work. And that's because our friction force is our centripetal force here. Remember, centripetal force means any force that's pulling you towards the center of the circle and causing you to turn. So that's what your friction force is. It's your centripetal force. So my friction force is equal to mv squared over r. Or I could write it as my centripetal force is equal to m times AC. Because both these two are equal to your centripetal force. So I'll do that one. So my friction force, I'll just make it times M equal to M times AC. So I plug in the mass which they gave us before, which was 615 kilograms, and I multiply that by the answer here, 9.68 meters per second squared. If I use this one, I would have just used my same V and my same R. I'm going to end up in the same spot no matter what. But let's see, 615 times 9.68, and I got 5,950 once you round to sig figs. So that's my friction force. That's also my centrifugal force. All right. Flipping it over. Question 2. An athlete whirls a 7-kilogram hammer that's tied to the end of a 1.3 meter chain in a horizontal circle. The hammer makes 1 revolution in 1 second. Similar to last time, 7.0 kilograms is my mass. My radius here, because I'm whirling it around in a circle, is 1.3 meters, and the time is 1.0 seconds. They asked me to find centripetal acceleration again. I'm going to run into the same issue as before. I don't have V. So again, I'm still going around in a circle. So V is still equal to my circumference divided by time. So I could plug in 2 pi times 1.3 meters divided by 1.0 seconds. Get my calculator. 2 pi 1.3 divided by 1. Oh, that was silly. 2 sig figs here, so we'll do 8.2 meters per second. So now I could substitute in, because I have my speed, 8.2 meters per second squared divided by radius. So 8.2 squared divided by 1.3. I should get an acceleration of 50 AC equals 52 meters per second squared. So again, important to remember, you can still have acceleration if you have a constant speed. And now they're saying find the tension. Well, my force of tension is going to be equal to my force of centripetal, because my tension is what's pulling the hammer, causing it to go in a circle. So Ft is going to be equal to M times AC, or you could do Ft is equal to mv squared over r. Either way, I like this one because it's just less to write. So my tension is equal to my mass, which is 7.0 kilograms, multiplied by my acceleration. So 7 times 52, I get a force of tension of 360 newtons. Again, they just use 2 sig figs. I don't know why I'm going with it so much today, but I am. 364 newtons on the calculator. To review, I'm showing all my work, all my units, just like you guys should. Send that one away. Question 3. Tom has a mass of 70 kilograms and Sally has a mass of 50 kilograms. Tom and Sally are standing 20 meters apart on the dance floor. Sally looks up and sees Tom. She feels an attraction. If the attraction is gravitational, find its size. Romance. So, force of gravity is equal to big G, M1, M2 over R squared. Whenever you have two masses, no matter where they are in the universe, they're going to obey this law of gravitation. So normally we do planets, satellites, moons, stars, blah, blah, blah. But this one's fun. It's about people. And we know they're not going to be, poof, like gravitationally attracted. It's just a joke, guys. It's a joke. They're in love. Someone has a crush on one another. Okay? It's funny. You're laughing. FG, where do we get big G from? Well, we get it from the reference table on the front page. Okay? And that is, it's actually the first thing on the reference table. So it's 6.67 times 10 to the negative 11 newtons times meters squared divided by kilograms squared, multiplied by M1 is 70.0 kilograms, multiplied by M2, which is 50.0 kilograms. All of that divided by the distance between them squared, which is 20.0 meters squared. All right, so get your calculator and get ready. So 6.67 E, and again the E key, you're going to hit the second function above the 7. That's on a TI 30 or a TI 89. If you have TI Inspire, it's the key on the left of the A. But by doing that, you don't have to multiply by 10 or do any carets or any parentheses. So you just do the E key and then hit negative 11 times 70 times 50 divided by 20 squared. No parentheses anywhere. As long as you type it all in correctly, you'll get the right answer. So 5.8, round it to 3 digits, 4 times 10 to the negative 10 newtons. So that's the size of the gravitational force. Is this the force or the attraction you feel? Of course not. But it's still there. Question 4, you got 2 bowling balls. No romance here. Each have a mass of 6.8 kilograms. They are located next to each other with their centers 2.18 centimeters. Dun, 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 dun. Is that good? No. So R, we're going to convert. It's 0.218 meters. We do not use centimeters here because they're terrible. But we need to find our gravitational force again. Big G, M1, M2 over R squared. All right, big G is 6.67 times 10 to the negative 11 newtons times meters squared divided by kilograms squared. Then we do mass 1, which is 6.8 kilograms, multiplied by mass 2, which is also 6.8 kilograms. And now divided by the distance between their centers, which is 0.218 meters. Square that value. Right, all my units, all my substitution, equation, everything's looking good. 6.67 E, again, it's above the 7 on the TI 30 and the TI 89. It's to the left of the A, the newer models. You don't need any parentheses here, or times 10 or carets. Times 6.8 times 6.8 divided by 0.218 squared. Oh, this is a good example. Now, you don't need to count. You just, whatever comes up on the calculator, we use 0, 0, 0, 0, 0, 0, 0, 6, 5 newtons. 1, 2, 3, 4, 5, 6, 7, 8. All right. 1, 2, 3, 4, 5, 6, 7, 8. Good. If you wanted to, or you could write FG is equal to 6.5 times 10 to the negative 8 newtons. I would just leave it how it is on the calculator. Okay? So that's that one. These two great gravitational problems. Sending them away. Alrighty. Home stretch here. A coin is placed on a final stereo record making 33 1/3 revolutions per minute. Find the magnitude of the acceleration when the coin is placed. Alright, so your acceleration is equal to v squared over r. But like before, we don't know. We know what r is. It's right here. But we don't know what v is. So v is equal to your circumference divided by time. So your circumference we know from the radius, and the time is we need to figure out. So we need an amount of seconds. So how long does it take to do one spin? It does 33 1/3, so 0.3 revs in, let's see, 60 seconds, right? Because 1 minute, yep. So 60 seconds. So that means that 33.3 divided by 60, it makes 0.555 revolutions per second. So if I want to know how much time it takes, I got to flip that. Oh yeah, so I should have done it this way. It takes 60 seconds to do 33.3. I did it upside down, my bad. Revolutions. So I want to do 60 divided by 33.3. So it takes 1.8 seconds to do revolution. So that's the time we're going to use. That's a crazy start we're not going to do something that crazy for the start here. We will do this kind of stuff. I don't like centimeters, so I'm going to convert that by moving it 2 decimal places. So 0.05 meters divided by 1.8 seconds, because that's the time it takes to do one lap. So 2 pi 0.05 divided by 1.8. I get a very low velocity of 0.1. How many digits am I keeping? 2 meters per second. Now, since we're here, I guess I'll just do this process over in a, like, kind of a 2-column this thing. So 2 pi r over t. So now my radius has doubled. It's at 0.1 meters. But the time is still the same because it's 1.8 seconds. Times 0.1, delete that value, divided by 1.8. So now my velocity has increased to 0.35 meters per second. I'll do it again down here just because we're on a roll. Oh, 0.15 meters divided by 1.8 seconds again. Go to my calculator, get my answer. Divide by 1.8. So V is, we're really getting now. And this makes sense. The further away we get, small loop, middle loop, bigger loop, the further away we get, we're still taking the exact same amount of time to do one lap, but now we're covering more distance because we have a wider circle. So I can get my acceleration for each. So AC is equal to my velocity, which is 0.17 meters per second squared, divided by my radius, which is 0.05 meters. AC, 0.17 squared, divided by 0.05. I got 0.58 meters per second squared. Same thing here. Man, I really made this repetitive. My velocity I found right here, 0.35 meters per second, divided by my radius, which is 0.1 meters. AC equals 0.35 squared, divided by 0.1, 1.2 meters per second squared. And the last one, same process, same equation. I have my velocity over here, 0.52 meters per second. Square that value. Divide by the radius. And for that one, that's 0.15 meters. AC equals 0.52 squared divided by 0.15. We got 1.8 meters per second squared. Again, these all trend in the right direction. A larger speed, a larger angular acceleration. Oh, this is your homework, not in this video. All right, last one. Assume you have a mass of 50 kilograms. What is the gravitational force of attraction between you and Earth? I love this one. What a one to end on, because I could do this, big G, M1, M2 over R squared. Or I could do this, mg, because whenever they don't say anything specific, we can assume that we're on Earth's surface. So this was just a throwback to how we used to do it. A little remember where you came from kind of thing. So we just do 50 kilograms times 9.81 meters per second squared. Now if you did this way, you'd have to use the mass of the Earth and the mass of you and then the radius of the Earth. All of these numbers are on the reference table. But I'm just doing this way. It's my shortcut. This is how we always used to do it. So 50 times 9.81. So you get 491 newtons. Love this one. What is your weight? Well, your force of gravity equals your weight by definition. Check your reference table. It says that. So your weight, oops, I almost started writing force of gravity again, is equal to 491 newtons. All right, so there you have it. Looking good. Woo! All right. Thanks for watching. Hopefully that helped. I think I'm going to go home now.